Forgot to record this. Are we actually missing anybody? We've got a full house. Okay, it doesn't matter so much. All right. So there is, in fact, a pretty direct and clear relationship between the change in their kinetic energy and the work that a thing is able to do. If you think about this in the context of traffic accidents, that's the other one. A low velocity collision is much less damaging than a higher velocity collision because the amount of work that gets done on the objects involved, being the car and its passengers, is lower. So remember, velocity is important. So the derivation is on your notes, but I'm going to have you walk through this with me step by step. So we all agree that work equals force times distance times cosine theta. Yeah? Okay. Would you also agree that force equals mass times acceleration? Yeah, good. Me too. So we can plug that in and say work equals mass times acceleration times distance times cosine theta. Is there another way to express the concept of distance? Think back to chapter 2. Could we say, in fact, that distance is really delta x? Yeah, that's not unreasonable. So work equals mass, acceleration, delta x, cosine theta. So far, so good. I want to pull out one little piece here, which is a delta x. And if you think back again to chapter 2, to kinematics, we ran across this. Vf squared equals Vi squared plus 2a delta x. Is there a way to solve that for a delta x? Yeah. Why, of course there is. So Vf squared minus Vi squared, whoops, divided by 2 equals a delta x. Okay, so work equals mass times Vf squared. I didn't color code that one. Is that okay? You good with that? I'll color code it for the visual learners out there. Okay. Vf squared minus Vi squared over 2, the whole thing times cosine theta, where theta is the angle between the force and the displacement. Okay, well now we're going to borrow this and take it to the next page. Take it to the next level. No, just the next page. So let's go ahead and do some distribution here. So work is equal to, well, that would be mass, final velocity squared, minus mass initial velocity squared over 2 times cosine theta. Is there another way to express that? What about work equals 1/2 final velocity squared minus 1/2 mass initial velocity squared whole mass times cosine theta? Well, recall that Ke equals 1/2 mass velocity squared. And if you had an object that's velocity was changing, well, this would be its final. This would be Ke final, and this would be Ke initial. Whoa, cool! Because what we're saying is that, in fact, let me shrink all this. The work that's done on an object is equal to the final Ke minus the initial Ke, and of course times the cosine of theta, where theta is the angle between the force at which it's applied and the direction which the thing is moving. This is the kinetic energy work theorem. And so what this allows us to do is look at an object that's striking another object or having a force acting on it, look at its initial and final velocity and figure out how much work is done. It also allows us to do plugins such as to take these two things, and actually I guess we do drop the cosine theta there because we end up with a sine thing anyway. What it allows us to do is say FD cosine theta equals 1/2 MVF squared minus 1/2 MVI squared. So it allows us this neat trick where if we have any piece of that, we can then solve for any other piece of it. So let's do the sample problem together, and then I'll give you time to work on the book problems. Okay, so we have a sled on a pond. Sled weighs 10 kilograms. Person kicks it across the ice, gives it an initial velocity of 2.2 meters per second. How far does the sled move if mu k is between the sled and the ice is 0.10? Oh, well, there's a lot of stuff there. So they've gone ahead and listed the variables. I'm going to list them again. So mass of the sled is 10.0 kilograms. VI of the sled is 2.2 meters per second. What's the final velocity of the sled that we're interested in? 0. We want to know how far it goes, so we want to know where it is when it stops. So VF equals 0.0 meters per second. Mu K equals 0.10 meter, or I'm sorry, no units, mu K. Whoops. Somebody asked me on the last ones, do I have to draw a Freebody diagram? I said, well, if you need to. Here you need to, because we need to understand what forces are acting on this sled. So we know that the sled has a VI. We know that it has some amount of displacement, or delta x, which is what we're interested in. And we know that there's a force of kinetic friction on it. Is there any other force acting on this on the axis where the motion is occurring? No. Huh? There's gravity, but that's on the y. There's normal force, but that's on the y. Okay, so let's start out with what we've got. Well, we know that work done on the sled equals the force, the net force on the sled, times its displacement, times cosine theta. In this case, cosine theta is going to be, what's theta going to be? They're opposites, 180. We also know that the work done on the sled is equal to 1/2 the mass times the final velocity squared minus 1/2 the mass times the initial velocity squared. And we know that final velocity is 0, so that goes away. That's awful nice of it. So what we're left with is this and this that we can set equal. So the net force times the distance the sled moves times the cosine of theta, where theta is going to be 180, is equal to the negative of 1/2 mass VI squared. So let's remember what we're solving for. We're solving for D. So I'm going to go ahead and rearrange here. D equals negative 1/2 mVI squared all over F net cosine theta, where theta is going to be 180. Am I done? Oh, of course not. Because there's a catch. They didn't give us F net, but we know what it is, and they gave us mu k. So this is where we have to go back to this. Mu k equals Fk over Fn. Mu k Fn equals Fk. Well, what's Fn here? Well, if I add, let me pick another color. If I add those, and I do a very quick little sum of forces on the y equals 0, equals Fn minus Fg, I can pretty quickly prove that Fn equals Fg. And are there any other forces on the x-axis? No. And again, I can do this using my x-axis. Sum of forces on the x equals F net, that's the direction of the motion, and it equals Fk. There's nothing else there. And I'm not worried about its acceleration. I'm not going there. We could, but we're not. So therefore, D equals, and I'm going to go ahead and move that 2 down, so negative mvi squared over 2 fk cosine theta. Well, I know that fk equals mu k fn, d equals negative mvi squared over 2 mu k fn cosine theta. Okay, so this is, I promise, the last step. What does Fn equal to? Well, Fn equals mg. So D equals negative mvi squared over 2 mu k mg cosine 180. And I went ahead and put the 180 in there. I could cancel out my masses, and I did that when I solved it. It just makes it a little cleaner, though it shouldn't change your answer, obviously. So let's do the plug-in. So D equals negative 2.2 meters per second squared over 2 times 0.1 times 9.81 times cosine 180. What do you get? So 2.46 on and on and on and on. The negatives top and bottom cancel out because the cosine 180 takes care of that. So we get 2.5 meters is how far this sled travels after we adjust for sig figs. I think we had 2, right? Yeah. That's it. All these problems are a little bit different. These are a little bit more challenging than just kinetic energy. Kinetic energy is like 3rd grade math for you guys. These are a little bit more challenging because you have to take multiple pieces and put them together in sort of unusual or creative ways. It's just substitution. You've done it before. So all the practice problems are assigned, and that's it. Get moving.